Yeah, so we were discussing the idea of universal quantum gates, right? And this will probably be the last lecture on gates and universality. And starting next week, we'll get into algorithms, right? Um, so we were discussing a few aspects of quantum circuits. So first of all, I think I need to recap a little bit because it's been more than a week since we had a lecture. So we looked at single qubit gates, and we said these are unitaries which belong to what is called the special unitary group. Doesn't matter so much, it's just that they form a group under multiplication, right? And then we looked at rotation gates, which are a special class of single qubit gates, right? And we looked at rotation about x, y, and z axis in the Bloch sphere. And that's why we call these gates as Rx, Ry, Rz. And we noted that any u belonging to SU2 can be decomposed in terms of either Rx, Ry, or Ry, Rz, Rx, Rz, right? So this is the one we showed because it was easy to prove this, right? Simply from the fact that this matrix forms a unitary, this 2 by 2 matrix is unitary. Just from that, we were able to prove this, right? And then we started looking at multi-qubit gates. In particular, we looked at 2-qubit gates, right? And we looked at the class of controlled unitary gates. Okay, and we said that 2-qubit gates, you could either think of local 2-qubit gates, which are simply of the form some U1 tensor U2, and then you have the truly non-local gates, of which the controlled unitaries form a particularly important class. Another important non-local gate that we discussed was the swap, right, which swaps the states of 2 qubits, right? And I think we discussed how these can be written in terms of each other, in particular how the swap can be realized in terms of controlled NOT gates, right? And so this pretty much is all that we need in order to talk about universality, okay? And that is the crux of what I will show you today. Let me just finish this whatever I wanted to say about universality first, and then we'll tie up a couple of loose ends. I want to also discuss a 3-qubit control gate, which can also form a universal gate. So we'll discuss all of that towards the end of the lecture. So let me first state and at least partially discuss the universality argument. Okay, so what is the meaning of universality? First of all, we know that in the quantum case, universality is not an exact statement. Okay, it is only an approximate statement. Unlike in the classical case where you say that a single gate can realize any Boolean computation, right? For example, the NAND gate, right? So any Boolean computation, which means any Boolean function, can be realized as a sequence of NAND gates, can be realized as a sequence of NOR gates. That's the kind of universality statement that you have in the classical case. But unlike that, in the quantum case, this is how we are going to define universality. So this is the definition of universality, which is that a set of gates maybe there are capital N of them, we'll see how many gates we need, is said to be universal if any arbitrary quantum gate and note that by this we mean of any dimension, right? So on any d-dimensional space, okay, can be approximated and this is the key difference. This is a key departure from the classical universality statement. You don't say that a gate is said to be universal if any Boolean function can be approximated by this. We know that you can exactly realize any Boolean function in terms of just the NAND operation or in terms of just the NOR operation. There are proofs for this, right? Here we are only going to say can be approximated to arbitrary accuracy by a quantum circuit comprising of these gates. Okay, so I hope the statement is clear. We want to identify some small set of gates in terms of which you can approximate any unitary operation, right? And that is the universality statement in the quantum case. You are not going to have an exact universality statement because the set of operations now is not some discrete set of operations like the set of Boolean functions. It is a continuous family of operators, right? It's a continuous parameter. It's a group that is parameterized by a set of continuous variables, right? So this, we are not going to get an exact statement. We are only going to get an approximate statement, okay? Now the proof of this, which I'm only going to outline, okay? And I'm not going to go into the details. That will take us a whole set of lectures to completely work out to completely prove this statement, because now you have to define what do you mean by arbitrary accuracy, how approximate, etc., right? So we will quantify some of these things, but not everything today, okay? So first of all, I should say that does there exist, so in the early days of quantum computing, this was an important question actually to address. Does there even exist such a set of gates, right, for which you can make this statement? So let me first say that the answer is yes, there does exist such a set of universal gates. So one set of universal gates is this set comprising of the Hadamard, the phase gate, the T gate, which is the what we call the pi/8 gate, and the C naught. Okay, so this is one standard set of universal gates, right? Now, two of these gates in this set are redundant. I mean, it's enough for me to actually write down 3 gates instead of 4. Which is the pair that is redundant? Because one is just the square of the other. Which are those 2 gates? Since you are fresh from the
A
midterm exam.
and T.
Exactly, good. So which is the square of which? So S is 100I.
S is the square of T.
Correct. And T is 100 e to the I pi by 4, right? So S is T squared, okay? So it's actually sufficient to just talk about HS and C naught, or rather HT and C naught, okay? There are also other relations. You must have seen some of these circuit identities, at least in the midsem. But some set C naught plus some pair of these 2 gates, right, is a universal set. Universal again does not mean that every unitary can be exactly decomposed in terms of these. It can be approximately decomposed to a high degree of accuracy. Arbitrary accuracy just means that to a high degree of accuracy, right? You can use a sequence of gates from this to approximate any unitary operation. So this proof actually is a 2-step argument. Okay, first of all, I should state that this particular set of gates showing that they're universal, I'll also upload a few references on Moodle. It goes by the name of this famous result in quantum computing called the Solovay-Kitaev theorem, okay, which actually quantifies how big a sequence you need if you want a particular accuracy, right? So this again, I'm just going to refer you to chapter 4 of Nielsen and Chuang. where they have a detailed argument of this. Unfortunately, we don't have time to cover this in detail, but it's a very nice argument. And it realizes, I mean, it uses the fact that some of these gates can be used to construct rotations on the Bloch sphere about arbitrary axes. Okay, so that's what the proof basically relies on. But this is just the final step of the proof, is the Solev-Kittel theorem. There are a couple of steps before that which we can try to understand, which are simpler to understand, let me say. So there's a two-step proof for this universality statement. The first step is to say that an arbitrary unitary can be exactly realized as a sequence, and by sequence I mean a product, right, of single qubit unitaries and C naught. So essentially what we are saying is that there is a larger universal set that we can first consider. Okay, and that larger universal set is the set of all unitaries in SU2 and C naught. Now, obviously, this is not a finite set. What is more, it's a continuous infinity. It's not even a discrete infinity, right? So this cannot really be a universality statement, but this is the first step to decompose. So essentially what you've done is you've reduced the complexity. So why do I say d-dimensional unitary? Because even if I just imagine qubits, forget higher dimensional quantum systems, even if they're just qubits, right? I may want to do operations like this, right, which involve 3 qubits, right, where this, okay, so this particular operation, for example, is what is called a controlled knot. Okay, it's a 3 qubit gate. Which controls this qubit. So this is the target, and this now has 2 controls, and the target flips if and only if both the controls are set to 1. This is also often called a Toffoli gate. Okay, so this is one example of a multi-qubit gate. If I write down this unitary matrix, this is going to be a 8x8 unitary matrix. So I should have a way of decomposing such an 8x8 unitary matrix in terms of single qubit unitaries and C naught, right? So you've reduced the complexity of building quantum circuits to being able to realize just one 2 qubit gate. Note that you have reduced it to just one 2 qubit gate and some set of single qubit unitaries. Of course, this set now says you need the ability to implement any arbitrary single qubit gate. Now that again is, a very tough ask. So the second step of the universality argument is to say that now any single qubit unitary which is U belonging to SU2 can be now approximated. Now is where the approximation comes to arbitrary accuracy using H, S, and T, right? So this is purely a single qubit statement now, right? And this, in fact, is going to be the harder statement to prove, okay? I can give you a set of, I can break it down into a set of questions, and I've often given a problem set based on this. I've not yet decided whether I should do that for you, but it is a bit of a hard statement to prove, right? The single qubit part. But the first part is simply some matrix algebra. And I thought I'll just show you that bit of matrix algebra for the first part. Okay. So by the way, this controlled not is also an important gate. Like I said, it's called the Toffoli gate. And there is also an alternate, I should just mention here as an aside, that an alternate set of universal gates is to use simply the Hadamard and the Toffoli gate. Okay. So this statement has also been shown that the same identical universality statement that any arbitrary unitary can be decomposed as a sequence of to arbitrary accuracy using simply the Hadamard and the Toffoli gate. Now this of course seems like a very compact gate set and a much nicer universal set, right? Just two gates. However, this Toffoli gate physically is rather hard to realize. It's a 3-qubit gate, right? It's hard to get this accurately. Although there are some architectures where this turns out to be a very natural gate. Okay. The Hadamard itself is actually not a very natural gate to realize. And what I don't know if all of you attended the IBM-Q lecture and whether you had a chance to make an account and try out things. But you will see that an IBM Hadamard is itself decomposed as some sequence of gates. It is not a native gate, right? So often people rely on this universality statement, this set of gates, because it turns out that the C0 is much cheaper to realize. And like I said, the single qubit gates, S and T, are not so hard. Well, in the sense they can be easily decomposed as rotations. And the Hadamard also can be realized as some sequence of rotations. Okay. Fine. So let's just go over this first part of the proof, which is the exact universality part, right? Because that already reduces the complexity of the problem enormously. So the key idea here is to reduce an arbitrary D cross D unitary to a two-level unitary. I mean, not just one, but actually a sequence or a product of two-level unitaries. So what is a two-level unitary? A two-level unitary is something, so I should also explain what a two-level unitary is. It's something that acts non-trivially only on a 2-qubit subspace of the d-dimensional space. Okay. So the idea is that you have some d cross d unitary matrix. Now, this of course will be realized only as a product of several d cross d matrices, right? But now the idea is to break it down into a sequence of d cross d unitaries which act non-trivially only on some two-dimensional subspace. What does that mean? Means that I have a d cross d matrix whose, for example, only non-zero entries are these four, everything else is zero, right? So this matrix, you can note, acts non-trivially on only two vectors, right? This acts non-trivially only on two vectors in the d-dimensional space. And that's why it acts non-trivially only on a two-dimensional subspace of, two orthogonal vectors. So it acts non-trivially only on a two-dimensional subspace of the d cross d space. Another example could just be, so you just have to pick some 4 entries like this, right? And that would be another example of so I should say that, of course, your diagonals cannot be 0. It's a unitary matrix, right? So something like this, right? Another example could be, let me just try to write down something else. Yeah. So you could have something like this, okay, with all ones here and everything else is 0, right? And so on and so forth, okay? So let me just give you a more concrete example of this. So these are all what we will call two-level unitaries, okay? Is the idea clear? Or maybe it'll become clearer with this example. So here's an example of a 8 cross 8 unitary. I mean, what you would essentially think of in some sense as a 3-qubit gate, okay? But this will be a 2-level unitary if it has this structure, which is exactly what I wrote down. So it will be A, 0, 0, 0, etc. So how many zeros do I need? Right? I put B here. Okay. So this is a unitary on a 8-dimensional space, which is a 3-qubit space. A 3-qubit space is an 2 to the 3, right? So it's an 8-dimensional space. And then, like I said, you need ones in the diagonal and everything else is 0. Now you know your 3-qubit computational basis states, right? So which are the, so you know that the normal 3-qubit space, I mean the full 3-qubit space is an 8-dimensional space and it is spanned by this set, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. 1, 1, 0, 1, 1, 1, right? Some set of 8 vectors, 8 orthonormal vectors. These form the basis for this space. So now can you tell me, we have a standard notation for these, right? Which are the 2 vectors from this set on which this unitary acts non-trivially? By non-trivially, I mean that those are the only 2 vectors which are not killed by this unitary, which are not destroyed by this unitary. All the other vectors, this unitary simply gives 0, right? So can you identify which are those 2 vectors? Which are the 2 states on which this acts non-trivially? Oops, sorry, I don't know what happened.
0, 0, 0 and 1, 1, 1.
You're right. Wait a minute. I don't know what happened to my notepad. Just give me a second. Yes, yeah. Well, I hope I've not lost everything I've written in the last. Okay, thanks. Good. Just give me a second. Just save my journal app suddenly started acting up. Okay, good. So you can see my screen now, right? Yeah. Okay. So an 8-dimensional space. That's what I was going to say. So there are 8 orthonormal vectors that span this space. And this is the set which goes like this. All right. So now what was your answer? Which are the 2 vectors on which this acts non-trivially or which does not give a 0 of those 2 vectors?
Get 0, 0, 0 and get 1, 1, 1.
Exactly. So U acts non-trivially only on 0, 0, 0 and 1, 1, 1 out of this 8. Right? Because we typically associate 0, 0, 0 with this vector and 1, 1, 1 with this vector, right? So you can notice that these are the only two vectors on which this acts non-trivially. And in fact, it essentially, so on this, so I can think of, okay, so I can think of this two-dimensional space, right? So consider this two-dimensional subspace. I hope everyone knows what a subspace is. I don't think I formally defined it in the early lectures. It's basically a smaller part of this space, right? So it's something which lives inside this C2 tensor, C2 tensor, C2, which is the 3-qubit space, right? It's a two-dimensional subpart of this 3-qubit space, and consider this two-dimensional space which is simply spanned by 0, 0, 0 and 1, 1, 1, which means you only consider states which are combinations like this, right? So in effect, this is like a ket 0 for you. If you want, you can call it 0 tilde. This is like a ket 1. So in effect, this is like a qubit space, right? This is like a single qubit space because it has only two. This is a space. So if I think of this full thing as my 8-dimensional space, this 2-dimensional space is sitting here. This is the full 8-dimensional space, right? So on this 2-dimensional subspace, it's effectively the space of a qubit because there are only a orthonormal vectors, and on the 0 tilde 1 tilde, the U essentially looks like this 2-qubit unitary ABC. I mean single qubit unitary ABC. Okay, so this is effectively like this. It effectively looks like this on the 2-dimensional subspace. The subspace spanned by 0, 0, 0 and 1, 1, 1. Okay, so U effectively looks like this in the subspace that is spanned by 0, 0, 0 and 1, 1, 1. Okay, so I hope this idea is clear. Now see how to do this. Okay, so I hope the idea is clear as to what two-level unitaries are. This is the effective form of this. So I can call it U tilde if you will. U effectively looks like this U tilde on this smaller subspace, right? U itself is a 8 by 8 unitary, but it is what we would call a two-level unitary because effectively it is like a single qubit gate on some subspace of this 8-dimensional space. Okay, so the claim now is that you can reduce any D cross D unitary as a product of such two-level unitaries and a C naught, not a C naught, but maybe several C naughts and C naughts. Okay, so let's look at that statement. Again, I may not have time to show the full proof, but I will just indicate. So we can show that if U is a D cross D unitary, then there exist two-level unitaries U1, U2, U3, etc., such that up to UK, let's say, this sequence or this product UK, UK minus 1, K minus 2, etc., U3, U2, U1 times U is identity. which then means that U itself can be realized as U1 dagger, U2 dagger, U3 dagger, etc. Okay. So basically there is some sequence of, note that if U is in a unitary, then U dagger is also unitary. I hope that that statement should be clear. So this is the sequence of two-level unitaries by which you can realize U. In a circuit implementation, this translates to a set of single qubit gates and CNOTs. Okay, so maybe I will add that in a circuit, this translates to a set of single qubit gates and CNOTs. Okay. Of course, these are now arbitrary single qubit gates, like I said, but that is what we need for the exact universality statement. And how are we going to show this? We're actually going to show this using an example. Generic example. So consider a 3 cross 3 unitary. Okay, now I'm kind of, so I hope I don't confuse you too much. See, I'm now talking about a 3 cross 3 unitary, which is not a 3 qubit unitary. So this here was a 3 qubit unitary, okay, which is on an 8 cross 8, 8-dimensional space. Now I'm talking about a 3 cross 3 unitary, okay. So it could be some unitary operation on a 3-dimensional quantum system. So a 3-dimensional quantum system is what you would call a qubit, right? So it's a unitary on a qubit system. The reason I'm doing 3 cross 3 is because it's the first non-trivial dimension after 2, right? And I don't want to do this whole matrix algebra for an 8 cross 8 unitary, but the same idea will go through, right? So please don't get confused with this jumping back and forth between qubits and higher dimensional systems, but let's just work this out for the simplest dimension other than 2, which is 3. So a general 3 cross 3 unitary, we can write like this, let's say. Okay, this is some 3 cross 3 matrix, right? So now we have to identify some sequence, right? U1, U2, U3, and in fact, we should know how many we need also for a given dimension, such that this statement holds. The statement that we wrote down here, so let me call this as 1, okay, such that 1 holds. So how do we identify? So there is an algorithm. This basically, I'm going to tell you an algorithmic approach to do this, right?
Just one question here.
Yeah.
So there is no upper bound on K as yet, right?
Not as yet. Once I show you the technique, you can tell me the upper bound. Okay.
Yes,
So this is somewhat similar to operations, matrix operations that you would have done in probably numerical methods and so on. Certain kinds of row reductions, column reductions, and so on. Right. Basically, I've already shown you the form, right? That you need. You need something which effectively has just 4 out of the how many ever entries to be non-zero, right? And the rest to be zeros, and of course the diagonals to be 1. And you have to show that you can decompose this as a sequence like that, right? So that's the goal. So the algorithm proceeds as follows. So the first step says, if D is 0, so it's possible that this element D is already 0, okay? If D is 0, then this U1, and now this U1, U2, U3, etc. will refer to this statement. Okay. So then U1 is simply the identity gate. Okay. If not, then U1 should be of the form. Now remember, U1, U2, U3, etc. should be two-level unitaries. So I'm going to populate these 4 entries and leave the rest to be zeros and ones appropriately. Okay. So what should these 4 entries be? Well, basically they should be of this form. A star means a complex conjugate. Okay. So I'm just going to write this down and then you can check that this procedure works. Okay. Probably need a bigger space. So you will see the pattern very soon. So then you will need what? The complex conjugates of these should be the other 2 entries because it's a unitary matrix, right? And this should be minus A. So this is one 2-level unitary. Okay. Now multiply U1 and U, or rather multiply U1 dagger with U and see what remains. Okay. So you can check now that if you multiply U1 and U, you will end up with a matrix like this, which has some other entries A dash, B dash, C dash, etc. But the key thing will be that this will make the entry which is here to vanish. Okay. You can of course start with any other entry also and the whole algorithm will work. And you will see that the last row essentially remains untouched. Okay. Because this has acted non-trivially only on this subspace. Actually, I'm not even sure if this involves C dash and F dash. I should check that. But anyway, so please check this out and also check if the C dash and F dash will be different from the C and the F. But the point is when you multiply this with this, because you have made this as A star and D, right? So what will happen? You will have A star D by square root mod A squared plus mod D squared. And you'll have a minus A star D over square root mod A squared plus mod D squared, right? So that is how this entry will vanish. So the point of the algorithm is to step by step make each of these off diagonal entries that you don't want to vanish, right? The next step will be to eliminate G. Okay, and for that you will need a similar structure, except that now the entries involved will be the outer 4 entries of the matrix and everything else will be 0. So now the second step of the algorithm is check if G is 0. Now if G is 0, U2, you will now have to have this diagonal entry coming in. So it will be of the form A dash 0 0 0 1 0 0 0 1. Okay. Yeah. Actually, I think you may need, okay, let me write this out and then maybe as homework, you can check if this works and tell me if I've made any errors of complex conjugation and things like that. So I claim that this should be A dash star. Okay. And if not, then once again, U2 will have a non-trivial structure with these 4 entries. Okay. This middle entry will be 1 and then these will be zeros. Okay. And what will those 4 entries be? They will again be of the form A star by square root. Now it will be mod A squared plus mod G squared, and it will not be A, it will be A prime, because the matrix has now changed to this form, right? It has changed to this form. So it will now involve A prime instead of A. So let me write this out. And once you have U2, you realize that you're more or less done because of the unitarity constraint. Okay. All right. So U2 is then of this form. We write this out of time. So it's A dash star mod A dash squared plus mod G squared, 0, G star, mod A dash squared plus mod G squared. And then these two, once again, you have A dash by this and minus G by square root. The same structure, complex conjugate and the negative sign here for unitarity. And then you can check that U2, U1, U, when you multiply all three, you will have a matrix where these two vanish. And then you will have some B double dash, C double dash, right? So now,
Addition G should be interchanged, I think.
where?
This U2 is equals to this A dash upon square root and G minus G upon square root. So I think minus G should be at the place of A dash and A dash should be at the place of minus.
You are right, you are right, you are right. Yeah, okay. And actually, I'm not sure where the minus sign should be, but let's see. Yeah, okay. Yeah, you are right. Yes. Sure. Yeah. So if you check now and multiply these three, so we have eliminated two of these entries. Now let me call this some matrix V. Now this is also unitary, right? And if this is unitary, then you can show that these two entries must also vanish. Okay, so actually if you check, this will be of the form, you'll essentially get something which is of the form 100, and you have E double prime, F double prime, H double prime here. But this again is another two-level unitary, right? And this is U3. Okay, so essentially what you will have is so I don't know if I want to call this U3 or U3 dagger, because the way we wrote down the statement. So now if you notice, you have U3, U2, U1 will be identity, because you see, what is this equation telling you? U2, U1, U is U3 dagger. So okay, let me write this out neatly again. So this is what I want to call it. I want to call it U3 dagger, so that I now have the statement. Okay, this in turn implies that U3, U2, U1, U is identity, which is the same as saying that U is U1 dagger, U2 dagger, U3 dagger. Okay, which is exactly what we want. So the idea is that you write down first one matrix which had these four entries and everything else 0. You write down a second matrix which has these four entries and everything else 0, and you end up essentially with a third matrix which has, sorry, these four entries and yes, right? So this was the structure of these four two-level unitaries, right? Sorry, these three, you have three two-level unitaries basically, and a sequence of this or a product of this gives you the desired unitary matrix. Okay, so now you can extrapolate from this and argue what you need for a D-level matrix. So is this itself clear? Is this idea clear? So of course this is, yeah, there are like these 2-3 steps that you have to check for me, okay? But the idea is to keep eliminating entries of your original matrix. And like I said, you could have started anywhere, right? You could have started, instead of wanting to eliminate D, you could have started with wanting to eliminate B, for example, right? It's just that we chose to eliminate this column, the first column, and then automatically this row has to vanish because of unitarity, and you're left with a 2 cross 2. You can do it the other way around also, right? You can do it with any two, any such rows and columns, right? You can, for example, think of D, B, F, H and try to make them vanish, and in the process you have, so the point is you have ended up with a set of 3 2-level unitaries, right? So there are 3 2-level unitaries. Okay. Now, so I will wrap up with just this last statement or this last argument to extend this for a D cross D case. Okay. So for a D cross D unitary, so let me call that as U sub D. Okay. Using D minus 1 2-level unitaries, I can get it to this form. So let's imagine that I do the same thing. Okay, I focus on the first row and the first column, right? Now, how many entries do I have in the first row here? So here I had 2 entries. So I needed 2 unitaries first, U1 and U2, and then I landed up with this form. So this, by extension, if I use D minus 1 unitaries, I can get it to a form where this entry becomes 1, all of these become zeros, all of these become zeros, but what I have out here is a D minus 1 dimension unitary, which means a D minus 1 cross D minus 1 unitary matrix. This is what we'll call U sub D minus 1. Okay. And now again, you do this procedure recursively. So the D minus 1 unitary UD. So UD required this. Now UD minus 1, you will need D minus 2 2-level unitaries, right? And you will get it to this form where there is now a D minus 2 cross D minus 2 unitary subblock, right? And everything else is 0, right? So you can now imagine doing this argument recursively until you really reach a 2 cross 2 subblock, right? So you have to do this all the way till you reach a 2 cross 2 subblock, which is U2, right? So this will be the last unitary in that sequence now, right? This will be your UK, the final K in that, right? So exactly, so what you will need, so now if I want to say that, so UD can essentially be written as, I'm now calling them V1, V2, okay, up to VK with, now remember this is an upper bound, okay, because yeah, indeed, so I think someone's making these observations in the chat already. This is an upper bound on how many unitaries you need, because some of these entries may already be 0. You may just get lucky, and like we said here, you know, if one of these entries is 0, you just need identity, right? So some of these matrices could just be identity matrices, right? And there could be other things which cancel out in these matrices. So finally, this is an upper bound, which is that you need D minus 1. You need at most D minus 1 2-level unitaries in the first step. You need D minus 2 in the second step, etc. All the way up to 1 unitary in the final step, right? So this is the 1 unitary in the final step. Okay. The second step, you need a D minus 2, etc. You will need 2 unitaries to go from U3 to U2. That's exactly what we saw here. So the example we worked out was to go from U3, which was 3 cross 3 matrix, general unitary matrix, to 2-level unitary. So you needed 2 2-level unitaries at that stage to get to this form, which was just 1 0 0 2 cross 2 block, right? So all the way from, so these are the numbers you have to add, is D minus 1, D minus 2, all the way down to 2, and then you have to add this final one unitary as well. So that's how you get the sum. And of course, as Siddharth has pointed out, this is indeed d times d minus 1 by 2. Okay. So in order to decompose a general d cross d unitary matrix as a product of two-level unitaries, you need at most d times d minus 1 by 2 unitaries, two-level unitaries. So remember now what I'm writing on the right-hand side, this bound, they're all two-level unitaries. And now the hope is that because a two-level unitary acts non-trivially only on some two-dimensional subspace of this larger space, I can simply realize it using a single qubit gate and some set of C nodes. Okay, so it looks like I'll have to show that only in the next lecture. So we probably have one more lecture on circuits. But so this is where I stop today. Okay, questions?
Just one question, ma'am.
Yeah.
So you said that two-level unitaries, as in they act non-trivially only on two states, right? Or two
Yeah,
gets
two
in the.
states, two orthogonal states, which is essentially like a two-dimensional subspace. Yeah.
So non-trivially in the sense that they don't get scaled back to themselves.
Correct.
So you don't
Yeah.
get the same state back.
Well, yeah, if you get the same state back, that's an identity matrix, right? So, and what I mean by non-trivially is it has support only on that two-dimensional subspace. See, if I act this matrix or this example that I had, where was this? See, if I act this matrix on any other column vector, right, which has a 1 somewhere in the middle, let's say, then you will see that you simply get 0, right? So for example, this U acting on 1, 0, 0, simply 0. Do you understand? Siddharth, right? Who asked the question?
Yeah.
So that
But
is
there
what I
is
mean.
also
So
the
this is
diagonal,
trivial action. It has no support on 1, 0, 0. Correct?
but there are ones on the diagonal, so you can't ever get 0, right?
Yeah, maybe I'm mixing this up. Okay, let me just check this out. Yeah, you are right. Wait. Yeah. So, okay, let me just work this out here carefully. Just give me a second.
Ma'am, what is the question?
Yeah, so his question was, what do I mean by non-trivial? So I claim that it has no support, but let me just check that I'm making sense out here. Yeah, you're right. So when I write this as an outer product, it is true that I will always have the, yeah. So when I write this as an outer product, I always have these entries. So I have a 0, 0, 0, 0, 0, 0 plus D 1, 1, 1, 1, 1, 1. Plus I have identity on the rest. You're right. Yeah, absolutely. Yeah, sorry about that. So I should have thought about this a bit more. Yeah. So this is one way of arguing this out, right? So I have C 1, 1, 1, 0, 0, 0, or the other way around. Plus identity on the rest. Okay, so I have this whole sequence which looks like 1, 0, 0, 1, 0, 0 plus 0, 1, 0, 0, 1, 0, etc. Right? So it's essentially identity on the rest. So you're right, Siddharth. Yeah. So what I mean by non-trivial is that it does not simply be identity, right? On the rest of the space, it is identity. So that's what it is. Acts as identity on the rest of the space. Is that clear?
Yes, ma'am.
Yeah. So Nilesh, was a question and answer clear?
Not very clear. I mean, the question is not clear.
No. So the point was, what do I mean by non-trivial? So I think I was earlier trying to say that it actually does not have support on the rest. But for that to happen, all these entries must be 0, right? And that will not be a valid unitary transformation, right? So for it to be unitary, I must have all these off diagonals to be 1. And then that means that it acts as, so this is a space on which it acts non-trivially, right? This little circle out here. What does it do on the rest of the space? It does not destroy the states. It basically acts as identity on the rest of the states. Because you see all the off diagonals essentially look like this, right? So they will leave all these states invariant. They will do nothing to them, right? So when I say trivial, I mean that it acts as identity, right? It acts trivially means that it acts like identity on the rest of the space. Okay, is that clear?
Yes.
Okay. Yeah, thanks for that, clarifying that. Any other questions? Okay, there are no further questions, then I'll wish you all a happy Dashera, and we'll wrap up for today, and we'll meet next Thursday, which is the 21st. Okay, and that'll be the usual class hour at 10 a.m. Okay. All right. See you all then. Bye.
Ma'am.